This video is on cis-trans isomerism. Cis-trans isomerism is specific to alkenes. Let's look at an example to see what we mean by it. Quick, name this structure. You may pause now. And here's the answer. And now name this structure. Pause now. And yes, you are correct. They are both 2-butene. However, they are different. For example, if we look at the dipole moments, one of them has a dipole of 0, whilst the other one has a dipole of 0.33. What about the melting points? Well, one of them has a melting point of negative 106 degrees Celsius, whilst the other has a melting point of negative 139 degrees Celsius. These are vastly different properties, and therefore we must be able to differentiate between the two stereoisomers. Enter the cis-trans isomerism. So we use cis and trans prefixes to differentiate between the two stereoisomers. Cis implies that both groups attached to either end of the alkene are facing the same side, whilst trans implies that both groups on opposite ends of the alkene are pointing towards opposite sides. For a cis-trans isomer to exist, A and B must be different and C and D must be different. The carbons of the double bond are referred to as stereocenters, as they are carbons at which interchange of two groups produces a stereoisomer. What do we mean by that? Well, if we switched places between A and B, we would end up with a structure that is different to the original structure, even though the order of bonding remains the same, i.e. they are stereoisomers. Let's practice some naming. So identify which of the following compounds have cis-trans isomerism and name them accordingly. You may pause now. And here are the answers. So what if we're asked to draw a structure, just randomly, and we're not given enough information? It happens to have an alkene in it, and it potentially could be a cis or a trans alkene. Which one should we draw? Or which one is better? Well, usually the trans one. Why? Because the trans tends to be lower energy. Cis structures have steric strain, whilst trans structures do not have any strain, or at least have less strain. And just as an aside, strain is any factor that destabilizes a molecule by deviating from optimal bonding geometry, i.e. we're not able to have perfect 120-degree angles on an sp2 carbon. So what about a structure with 3 substituents on an alkene, such as this one? Well, we can't name it cis or trans anymore, or at least not 100% without ambiguity, because we need to know what we're referencing. However, we can still use cis or trans as relative terms. So for example, we can say these two methyl groups are trans to each other, or this methyl group and this terbutyl group are cis to each other. More importantly though, we need to be able to tell whether this structure is more stable than this other structure. Well, clearly if the argument is about steric strain, then we would expect the bigger group to cause more strain. So it would make sense that having the methyl groups cis to each other will give us less strain, because the bigger thing is by itself. For steric strain, bulky interactions are always bad. Alright, final practice. Name these two structures and state which one of them would be more stable or lower energy. You may pause now. And here are the answers.